Okay, today we are going to be learning about the Poisson distribution. I'm pretty sure this is French. This is how you spell it. Okay, pronounced, I believe, if I'm understanding correctly, is Poisson. Okay, so traffic planning is a major concern. Okay, so if you've ever been to a big city, you know about traffic jams. Planning when the red lights turn, planning all these are very important. And modeling the traffic in terms of statistical distribution, it is possible to calculate the probability that the level of traffic through an intersection along a road is greater than a predetermined limit. Okay. So we can do this using statistics. So we're going to watch video. I want you guys to pause this video right now and watch the video in the book. This is 4.17.0. And because I don't think I can show this video on the recording. Okay. So please pause and watch this video here, traffic modeling. Okay, now that we've unpaused, the concept of probability distributions can provide a representation of relationships between theory and reality. These representations can make us make predictions about what might happen. And that is the beautiful use of this. So, before we talk about the Poisson distribution, we're going to review the binomial distribution because it's very similar. Okay. And binomial had kind of four conditions. And that was condition number one, two outcomes, often called success fail, but there's really no success to success. Two, each observation is independent. Independent. The probability of success is fixed, meaning it's the same every time, no matter what happened the time before. That kind of goes with independent, but this is just a little more specific. And this is the one that's not in the Poisson. I believe those first three are all the same. But with the binomial, you had a fixed number of outcomes. So we'd be looking for made free throws out of 20. Sometimes that's really practical, sometimes it's not. Okay? So our first example here is reviewing binomial. Correlline, so I'm going to get rid of those, write them in your notes, review them. But Corralline owns a red racing bike and a blue road bike. She only rides one bicycle each day. On any given day, there's a 70% chance that she will ride the blue bike. Calculate the expected number of days in which Corralline will ride the red bicycle in 1 year. Okay. So the chance of red is 30%. Okay. So if you remember, expected value is simply mean. And that is given by number of outcomes times probability of success. So there's a 70% chance she'll ride the blue, meaning there's a 30% chance she'll ride the red. We're going to go with a 365-day year since that's the majority of them, times 0.3. And I'll just let the book show me what that multiplies to be. 109.5. So you knew it was, remember, this is our shorthand notation for binomial, B number N P. Number of outcomes 365, 0.03 was probability of success. So that is binomial. We did that a month and a half ago, maybe. Important thing to remember. So the key aspect was 365 days. However, if you want to consider situations with an infinite number of possibilities, you need to use the Poisson distribution. There's a random variable that can be described as the occurrence of the events. So two assumptions are made when determining that the random variable follows a Poisson distribution. First, each independent is independent, or each observation is independent. For example, is assumed that the bike Coraline rides on a given day is independent of the bike she rode the previous day or the previous week, etc. Second, the mean value of the Poisson distribution is a number based on data gathered over a period of time. It is based on historical data. Okay? In the applet below, you can explore the distribution. The applet draws a histogram of a random variable of size n drawn from Poisson distribution of mean mu. So if we open this applet, so mu here is 23. If I move mu up to 40, see it's still centered around 40. Notice that this is actually simulated data. Notice that 40 is not the most common, even though that's the mean. Notice what happens when I shrink my sample size. It's generally centered around this, but definitely far from perfectly normal. Okay. So you can investigate the experimental values by changing A and B, dividing the number. So X is some value between A and B. And so this is, say, a cumulative distribution. There were 647. This is going, what's the probability of landing between these two? No, between 34 and 40, there were 239 possibilities. So given the limitations placed on the assumptions mentioned above, we can tell that the Poisson distribution model the real world. Consider the formula used to calculate for a Poisson distributed variable. X is PO of M, or P x equals X, where M to the X equals E to the negative M over X factorial. So be aware, Poisson distribution is based on the number of occurrences of an event. We'll see what X and M are in a little bit. Okay. You will not be expected to use this equation. You can use your calculator. Yay! If a random variable X is distributed such that X is a Poisson of M, then the expected value for x is the variance of x, which equals m. In other words, the expected value and the variance of the Poisson distribution variable are both equal to the value of m. So remember, variance is standard deviation squared. So, as m is a rate when determining whether to use m as a rate, when determining whether to use the Poisson distribution, it's important to identify the average occurrence of the random variable and what the change in the variable depends on. The table below gives us some examples. Visitors to the museum in a time interval. That's a random process. Event, the number of visitors per hour, time dependent. Random process, survival of migratory birds, number of birds touching down per hour, also time dependent. Flaws in laying a railway line, number of flaws per kilometer, that is length dependent. Red blood cell count, number of red blood cells per 100 milliliters, volume. So let's look at some examples. Akini is investigating whether a certain intersection needs to have a traffic light installed. She found that the average number of cars going through the intersection every minute during a workday is 33.2 cars. So that's 33.2 cars per minute. Traffic lights should be installed if the probability of there being more than 10 cars per minute in the intersection is greater than 10%. Determine if a new traffic light should be installed at the intersection Akini is investigating. So, first, we identify the parameter. So, the average rate is 33.2. So, m is 33.2. Poisson of 33.2. We're looking for the probability that x is greater than 40. So, see here, there's our m. It's given right here in the problem. That's the rate. X is greater than 40. We have to do the 1 minus case. The calculator cannot do the other one. So, I'll show you how to get this on various calculators in a second here. 1 minus 0.08947. So that's 10.5%. Oh, it's greater than 10. They do need a stoplight. Okay, how to actually do this on the calculator. I've got the Inspire open. Hold on, let me quick open the 84. I'll show you both. Okay, so on the Inspire menu, you can either go statistics or probability. Both of them have distributions. And we're going to look at a Poisson CDF. And here they're using lambda. So I'm looking for if it's more than 40. So I'm going to get less than 40 here. Lower bound has to be 0 for this to work right. That is my mean, 0.8849. If I go 1 minus answer, I get my 10.5. Hold on while it lets me log into the 84. And it's pretty similar, I believe. I'm going to see if I can hit one. Yeah, we'll just do. So, stat, nope. Distribution is second function of var. Poisson CDF, 33.2. It automatically does the bottom. And there, my answer for greater than is 1 minus, and there's my 10.5. Okay, that's pretty easy. We're going to be using CDFs. We're always going to be using 0 to the bottom. I tried doing it the other way on the Inspire, and I didn't get the same results. Okay. I think because it goes to infinity, it doesn't quite, you can't just cut it off because there's no fixed number of results. Okay. So, so this is common. This is used all over the place around the world. Um, as discussed in the article from the 30th Australian Transport Research Forum, one factor that capacity of a road depends on is the speed at which cars are allowed to travel. The maximum speed allowed on roads is determined by each country individually and varies per country and per state here and per area. And it has to do with how many people are around and intersections. And there's a lot of factors that are involved in that. But one way to make better flow is allow traffic to flow faster. As the event in a Poisson distribution is distributed, Poisson distributed variable occurs uniformly. They are proportional to their interval. Therefore, the value of m can be scaled to fit the new interval. Here's another one. Visitors at a museum arrive at an average of 2 per minute and follow a Poisson distribution. Find the probability that 12 visitors arrive in the first 10 minutes after noon. Okay. So my average 2 times 10 minutes is 20. This time we're going to use the Poisson PDF. My average was 20, 2 times 10 is 2 per minute. I'm looking at exactly 12, 1.7% chance. And again, they asked me about exactly 12, not 12 or less. 12 or less would be possible. And all of these are possible, just not real likely that it's exactly 12. Adding two Poisson distributions. The sum of two independent Poisson distributions. So when we have random variables, I can simply add the means. I cannot do that with the standard deviations. We don't have to talk about those. So means I can just add them. For a certain railway, it is found that the flaws on the railroad tracks from installation occur following a Poisson distribution. Due to the method used to install track, there are average of 5 flaws per kilometer on the right rail track, and only 2 flaws per kilometer on the left rail. In planning for a new 20-kilometer long track, the company wants to budget enough for repairs so that at least 95% probability they will be able to repair all the flaws on the new track. Determine how many flaws the company should budget for. So we know that there are 5 plus 2 or 7 per kilometer, and we can just add them up. 7 times 20 total kilometers is 140. So I'm looking at a Poisson of 140. So next, we're going to use our calculator to find the number of flaws for which the company should budget. Okay, so we're going to have to do this. So this one, I can't just do a single one. I could, they don't tell me what to guess and check here, do they? Did they do this in a list? So you can define on the Inspire, I think you can do this on the 84 too. Can define a variable and you can actually just put in the value X. Okay. So on the 84, on the Inspire, you do something like F, well, they're doing is, we'll do it like this. P of X, and they're going to use this colon equals. That is second function of the button next to 9. And now we're going to do a probability distributions. I believe it's a Poisson PDF. And this is going to be 140 here. X value is going to be X. Nope, it's a Poisson CDF. Sorry. So menu, probability distributions, Poisson CDF, 140. Going to do the lower bound 0, upper bound X. And then I am going to go to my graph. I need to get back to a function. And it looks like about nothing for a while. Now I know I have to be greater than 140. I'm going to also enter a value of 0.95. And I'm going to change my window. This is the rare case where I do not want to adjust the Y's. I'm just going to go 200. I think it'll be there in less than 200. I did the wrong one. I'm so used to adjusting Y's that I adjusted the Y instead of the X. And we can see it kind of tapers off. And oops. Menu, analyze graph, intersect. And I get 160. 160 is 0.948. So I want at least. That. They've got slightly different. So they're saying 159. That one's saying 160. I will do, let's do it on the TI 84. We're just going to come here. We're going to go into Y equals, and we're going to go distributions from here. And we're going to go Poisson CDF. This is 140. That's going to be the X. And we'll hit paste. I hit 149. That's not going to do it for me. Now let's do it. I'm going to change my window appropriately. My max 30. I'm going to adjust my scale to about 10th that. I forgot to put 0.95 in here. And now I'm going to graph. And I will get my intersection with second trace. There's my two curves. I don't care what the guess is, it'll find it. And it had it at 160. And it said 0.956. I'm a little surprised the two calculators didn't quite agree. Somehow this ended off by 1. Let's see, did I program it right? I did. So, but roughly the same amount. Okay, that is the Poisson distribution. You're going to be using your calculator to calculate it every time. Okay, it allows us to come up with probabilities with not fixed amounts, which is really powerful. Okay, that is it for today's lesson.